Today's class, I will be teaching various theorems applicable for LTI systems. First is theorem for causal systems. Theorem for causal systems. Theorem for causal systems. I write the statement: a discrete time LTI system is said to be causal if and only if h of n equals 0 for n less than 0. IFF means if and only if. Given the statement for a discrete time system, a similar statement would hold good for continuous time system also. Instead of h of n, I will write h of t equal to 0 for t less than 0. Very, very important theorem. So now we shall prove this. Proof. Let us consider an LTI system having impulse response h of n, input x of n, output y of n. This is an LTI system. Figure number 1. Consider an LTI system. Consider an LTI system as depicted in figure number 1. What is the output of the system? Y of n equals what? X of n convoluted with h of n equals what? Summation k equals minus infinity to plus infinity x of k into h of n minus k. Now limits of summation I split in this manner. This implies y of n equals summation k equals minus infinity to n x of k into h of n minus k plus summation k equals n plus 1 to infinity x of k into h of n minus k. This I call as equation 1. What I have done is summation limit from minus infinity to plus infinity. I split from minus infinity to n, then from n plus 1 to infinity. You should not do a mistake by writing n here. The discrete time system. So after n, next limit will be n plus 1. That aspect you must not miss it out. According to the statement for causality h of n equals 0 for n less than 0. This implies, replace n by n minus k, h of n minus k equals 0 for n minus k less than 0 or k greater than n. This I call equation 2. Using equation 2 in equation 1, we get y of n equals, what happens is this summation will become 0 because this summation stands for k greater than n. K greater than n means n takes values from n plus 1 to infinity. Therefore, when you substitute equation 2 in equation 1, this summation will become 0. We get y of n equals summation k equals minus infinity to n x of k into h of n minus k. This in turn implies y of n naught. Put n equal to n naught. What you get? Summation k equals minus infinity to n naught x of k into h of n minus k. Please don't substitute or don't replace this n by n naught. Only in the limits you have to make the alteration. When you put n equal to n naught, only this n gets replaced by n naught. This n is not affected. What this equation means, output y of n at n equal to n naught is dependent on the values of the input x of k from k equals minus infinity to n naught. That means present output is dependent upon the present and past values of the input, hence the system is causal. I am going to write it down for you. This I call equation number 3. Equation 3 means output at n equal to n naught depends on the values of the input from minus infinity to n naught. That is present output is dependent on present and past values of the input. Hence the theorem. I'll write the remarks here. A continuous time LTI system is said to be causal. If and only if h of t equals 0 for t less than 0. A continuous time LTI system is said to be causal if and only if h of t equals 0 for t less than 0. Very, very important theorem. Most of the times asked in the examination. Next, theorem for BIBO stability. BIBO means bounded input, bounded output stability. Theorem for BIBO stability. BIBO means bounded input, bounded output stability. This theorem is applicable again for LTI systems only. A discrete time LTI system is said to be stable. Stable means BIBO stable. Is said to be BIBO stable if and only if its impulse response h of n is absolutely summable. That is S is equal to summation n equals minus infinity to plus infinity, modulus of h of n is less than infinity. What I said, a discrete time LTI system is said to be BIBO stable if and only if its impulse response h of n is absolutely summable. That is S equal to summation n running from minus infinity to plus infinity on modulus of h of n is less than infinity. Similar condition holds good for LTI systems which are continuous time in nature. Instead of summation, we have to put integration. Instead of n, we have to put t. That I will write in the remark section at a later stage. I am going to prove this now. Let us consider an LTI system having input x of n, impulse response h of n, output y of n. This is an LTI system which I call as figure 1. The response of the LTI system shown in figure 1 is y of n equals x of n convoluted with h of n, which is same as h of n convoluted with x of n. Why? Because of commutative property. This implies y of n equals summation k equals minus infinity to plus infinity h of k into x of n minus k. This I call equation 1. Let x of n be a bounded input. Let x of n be a bounded input. That is magnitude of x of n less than or equal to mx, mx less than infinity. This is what I mean by bounded input. This implies replace n by n minus k because I want x of n minus k here. This implies magnitude of x of n minus k less than or equal to mx, mx less than infinity. What I mean is, if you replace n by n minus k, mx doesn't change. In simple words, if you translate a sequence to write by k units, its amplitude won't change. Substituting equation 2 in equation 1, we get y of n equals, before I substitute, okay, I'll do a small modification. Taking magnitudes on both sides, of equation 1, we get modulus of y of n equals modulus of summation k equals minus infinity to plus infinity on h of k into x of n minus k. Applying triangular inequality. When you apply triangular inequality, what is triangular inequality? When you take this modulus inside the summation, this equal to becomes less than or equal to. So what I mean by that is applying triangular inequality. We get right here, we get magnitude of y of n less than or equal to summation k equals minus infinity to plus infinity modulus of h of k into x of n minus k. This modulus, once you take inside the summation, is equal to sign becomes less than or equal to. This in turn implies magnitude of y of n less than or equal to summation k equals minus infinity to plus infinity magnitude of h of k into magnitude of x of n minus k. This I call equation number 3. What I made use of here? Please remember, modulus of AB is equal to modulus of A into modulus of B. This aspect has been used on this equation. Next, what I am going to say is substitute equation 2 in equation 3. Substituting equation 2 in equation 3, we get magnitude of y of n less than or equal to summation k equals minus infinity to plus infinity modulus of h of k into mx. This in turn implies magnitude of y of n less than or equal to mx into summation k equals minus infinity to plus infinity modulus of h of k. See, k is a dummy variable. Therefore, k can be replaced by n. What I mean is, let us say you have got a summation on n square from -1 to +1. This is same as summation on k square from -1 to +1. It makes no difference because here n is taking the values, here k is taking the values. Therefore, even if you replace n by k, summation will not give a different answer. Same logic I will apply here. I am going to say k is a dummy variable. K is a dummy variable. Hence, it can be replaced by n. Then magnitude of y of n less than or equal to mx into summation n equals -infinity to +infinity magnitude of h of n. We find that magnitude of y of n is less than infinity if and only if summation n equals -infinity to +infinity modulus of h of n is less than infinity. Hence the proof. Very important proof for studying digital signal processing in the subsequent semester. I am going to write a remark. The remark is remarks. A continuous time LTI system is said to be Bibo stable if and only if, IFF means if and only if, its impulse response h of t is absolutely integrable. That is integration from -infinity to +infinity modulus of h of t dt is less than infinity. This condition you will be applying in control systems to study the stability of a system in frequency domain. Very important theorem for control systems. Only thing is, instead of h of t, there we will use g of t. And what is g of t? G of t is nothing but Laplace inverse of g of s. G of s was called transfer function. Inverse Laplace transformation of the transfer function gives impulse response g of t. And this has been used to show that in control systems, for a system to be stable, all the poles of g of s must lie on the left hand side of the s plane. Hence, when you ask your teacher why poles must lie on the left hand side, in order to explain that, your teacher has to refer to this equation. Last theorem, it is for memoryless systems. Theorem for memoryless systems. Theorem for memoryless systems. Statement: a discrete time LTI system is said to be memoryless. Memoryless means no memory. Memoryless if and only if h of n equals c into delta of n, where c is some arbitrary constant. I am going to prove this. For proving it, let us consider an LTI system having impulse response h of n, input x of n, output y of n. This I call figure 1. The response of this is proof. The response of LTI system shown in figure 1 is y of n equals x of n convoluted with h of n. Equation 1. If h of n equals c into delta of n, then y of n equals x of n convoluted with c into delta of n, which implies y of n equals c into x of n. The above equation means nth value of the output depends on the nth value of the input, and the system has no memoryless. The above equation means nth value of y of n depends on the nth value of x of n. Hence the theorem. Next I will say in the remarks, I will say what happens for a continuous time system. What happens for a continuous time system? Remarks. A continuous time LTI system is said to be memoryless. If and only if h of t equals c into delta of t, where c is some arbitrary constant. In the next video, I teach you the problems.